Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them to succeed in their careers and lives. In this episode, we are talking to Luke Pinkerton, a licensed professional engineer with a master's in engineering, who is the president, Chief Technology Officer, and founder of Helix Steel, about better ways to design and build with concrete by using advanced analysis, materials, and methods to design plain concrete and structural ground-supported slabs.
I'm your co-host, Matt Picardle.
And I'm your co-host, Kara Green. Now let's jump into our conversation of the week with Luke.
This episode of the Structural Engineering Channel is brought to you by PPI, a leader in engineering exam prep for the PE structural exam. PPI provides expert prep courses and study resources designed to help you pass the PE structural exam the first time. PPI's PE structural course is fully updated and taught with October 2021 code references and includes new editions of their PE structural books. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. PPI has helped engineers achieve their licensing goals since 1975. Check out PPI today at PPI2pass.com to see all of the resources available for PE structural exam prep. Again, that's PPI2pass.com.
Luke, first, welcome to the show. We're so happy to have you today. In your own words, could you tell our listeners a little bit about what you do and the work that you do?
Sure, Kara, but and Matt, thanks for having me. Really happy to have a chance to share with you. That's a good question, because what I do probably isn't what every, structural engineer studying to be an engineer in college is looking at. I kind of have a little bit of a non-traditional path. So just real briefly, I actually have an undergraduate degree in engineering physics, and then I have a graduate degree in civil structural engineering from the University of Michigan. And I kind of got a little frustrated in school with kind of structural engineering in general, because I was concerned that it would be a little bit too formulaic and too code driven. And at the University of Michigan, they have a naval architecture program there also. So they recruit people into naval architecture applications. So I actually ended up out of Michigan going and working for General Dynamics, designing ships for the US Navy. And if you think about it, it's kind of a cool structural engineering problem, because it's like a floating power plant that has all kinds of exotic load cases that are way worse than your maximum credible earthquake is in California, Matt. So and it's kind of alluring a little bit, because it's a little bit the sort of the secrecy aspect to it and all that, and being able to kind of go out on sea trials and things like that was pretty cool. But after a few years, I kind of realized that, a government job is kind of a government job. And, I wanted something more. So I went and got an MBA at Georgia Tech. And when I was at Michigan, the professors there were studying this Helix technology, which is a twisted steel micro reinforcement that you mix into the concrete. The technology had been patented, and nobody had licensed it. So I jumped at the opportunity out of my MBA program to license the technology from Michigan and launch a business around it. There were many challenges. The first was figuring out how to make the product, which was very difficult. This is a twisted piece of steel about an inch long, and you literally have to put millions and millions of them in to each concrete truck to be able to use it. And when we were at the university, we literally were making this with a drill and a pair of pliers, one by one. So I got involved with building a machine to do it. And, we were able to kind of figure that out, and then started the long process of seeking the market to adopt it. So to answer your question now, what I do, I'm the president and chief technology officer of Helix Steel. Helix Steel makes a product called Helix 525. It's been on the market for almost 20 years. It's a twisted steel micro reinforcement that you mix into the concrete. It's a discontinuous reinforcement that you mix into the concrete that increases the concrete's initial cracking strength, the modulus of rupture, and it also provides resistance after the concrete cracks. So my role really has evolved over time, but right now I do a lot of technical outreach. You know, the way that we sell our product is really mainly by seeking specifications from structural engineers. It's a very technical sale, so I support the sales team in that regard. And then I have a lot of business responsibilities that range from operations to, sales to, even manufacturing that I oversee. So it's a pretty broad responsibility. Structural engineering is probably where I add the most value because you can find people who know how to run factories and things like that, but the engineering piece is much more difficult. So I definitely encourage people that are interested in manufacturing and products, and anyone going into who's even interested in business to really hold on to that technical, avoid the temptation to just jump into business, because having that technical background really sets you aside from everybody else.
Yeah, thanks for that, Luke. I know there's a lot of even in the technology industries, lots of the CEOs and presidents like yourself do have those engineering backgrounds, and you can kind of see that pattern of how that engineering background leads to success, especially as you get into the leadership roles. Could you, for the structural engineers out there, could you explain a little bit what the plain concrete is and how it differs from reinforced concrete, maybe with regards to Helix Steel?
Sure. So structural plain concrete is actually something that's been around for, thousands of years. I talk about, sometimes the Pantheon in Rome. It's one of the largest, if not the largest, unsupported dome structure that's made of plain concrete. And you can understand how, as a structural engineer, it's a dome structure, which means it's principally in compression. But there's a lot of engineering that goes into that. So structural plain concrete, it's in chapter 14 of ACI 318. It is totally a permissible way to design. Technically, the ACI CT defines it as any concrete that has less than the code prescribed amount of rebar for reinforced concrete. It is designed elastically. So basically, unlike with reinforced concrete, where you essentially neglect the tensile strength of the concrete, you actually use it and you design based on calculating the stress basically at the point at which the concrete will crack in tension. So it's been in the code. It's not used that much because the code is very, very conservative on it. Basically, if you look at the resistance factor that's used for plain concrete, it's 0.6. Your load factors are between 1.6, 1.4, and then the code requires you to basically take half of the tensile strength of the concrete. So if you add all that up, you end up with a factor of safety around 4. So it's not really that efficient to use. What we've been able to do with the Helix product is because it increases both the amount of flexural tensile strength or tensile strength that you get, the modulus of rupture with the concrete, and it makes it more consistent. We've been able to show that we can use more. We can get more out of plain concrete than with just ordinary plain concrete. So what we do is we run the ASTM C78 flexural test. We characterize the tensile strength of the concrete, and then we use that value for design. So it's a form of performance-based design. We have an evaluation report that was done by the International Code Council Evaluation Service, ICCES, that uses that approach. And in essence, you can get about twice, sometimes a little bit more of the resistance out of what would technically be defined as plain concrete, Helix reinforced concrete, when you use the Helix and you use this performance-based approach.
So it's like it's still in per the code, it's still plain concrete, but if you put the Helix, is it an admixture? It's not an admixture, right? It's a type of proprietary
Like an additive?
Well, it's yeah,
steel,
that's a
right?
good question, and I've been purposely avoiding the word fiber. Some people would call it a fiber. It is a steel reinforcement. It's twisted. It's 1 inch long and about a half a millimeter in diameter. So it's similar to a steel fiber or like a synthetic fiber, but we call it micro rebar because it has the fibers typically don't do anything to the concrete until after it cracks, much like rebar. The Helix product is able to increase the amount of force it takes to crack because the bond is very good between the fiber and the concrete because of the twist. It creates load paths that can carry load before you have those large cracks form. So you get a boost there, and then it does behave more like rebar after the concrete cracks because of the failure mechanism that it has. It won't break in tension. It has to pull out, and it actually has to untwist a little bit as it pulls out. So it has a lot of advantages over a fiber, and we don't necessarily design it the same way. Most of the fiber industry will say that there is no effect on modulus of rupture from a fiber.
Oh, gotcha. But with at least with Helix, you've tested it per the ASTM standard, so you've proven that it can be have a higher modulus of elasticity, and that's why you can get higher values per ACI in the plain concrete section, right?
Right. It's the modulus of rupture. So, which is that flexural tensile strength.
Gotcha. Very interesting.
So we're getting a little technical, but I'm trying to kind of go ahead.
No, and I just had a quick question because you mentioned that this falls under ACI 318 chapter 14, which is specific to plain concrete. But I think of, some of the restrictions around, reinforced concrete today where, you do have to have like a certain amount of concrete width and depth in order to essentially cover your mesh appropriately. Do you know, would there be a scenario where you would utilize the Helix structural fiber, lack of a better term, the little mini rebars with an existing rebar mat and essentially a performance-based design just to achieve a higher modulus of rupture with a reinforced element?
Yeah, so I'd say probably most of the work that we do is going to be a complete replacement. So things like slabs on grade, footings, and things like that, we always aim to replace all the reinforcement because there's the maximum benefit to the end user and the folks doing construction. However, if you get into a heavier reinforced structure or sometimes structures that have vertical elements that need to have connections and things like that, we definitely will use a combination of the Helix and rebar. And there's an approach to design that's it's more similar to reinforced concrete design when we do that, because we're looking at sort of the condition after the concrete cracks.
Okay, good deal. That's awesome. I was just a little bit curious if they could be, as you mentioned before, sometimes the code is a little bit restrictive, and I was curious if you could mix the two and observe some of the benefits with the Helix ties or Helix structural steel connections. So I want to pivot a little bit because, we've been talking about Helix structural steel, and, you said that it's been on the market for 20 years, but it sounds pretty innovative in regards to really, I guess, better defining concrete and really observing some of the benefits that you can achieve with concrete, even though that the code seems to be a bit more restrictive. And something that Matt and I talk a lot about is around innovation and how we're seeing a pretty fair boom of innovation in the construction industry lately. And with that, we need engineers. You've had a very diverse and interesting background, and I can see some of the innovation with you specifically And you may be able to answer this question. So, how does the need for innovative engineers to solve new problems influence or impact specifically high material costs? Because both steel and concrete are very expensive right now. And it really takes a mind that can, I guess, solve these new problems that the industry is seeing around scarce labor or scarce materials, and of course, the carbon footprint. What are your thoughts on that?
Well, it's a great question, Karen. I've spent a lot of time working on this, and I mean, thinking, even within the context of structural plain concrete. I actually started a committee at ACI, or restarted a committee. And there was a committee that was active in the 1950s and 60s on structural plain concrete. And there's a gentleman there who was leading it. He was with Albert Kahn, architects out here in Detroit, that was really very passionate about, advanced materials back then. And there were better performance-based provisions in the code to allow the use of advanced materials at that time than there are now, believe it or not. So I reached out to ACI and I said, look, we've got all these challenges. We need to have better ways to provide a pathway for industry to innovate. It takes both. It takes engineers who are willing to innovate. And this goes back to my frustration when I was in structural engineering school, because I felt like some of the classes were like, okay, it was more teaching, I felt, and I know this isn't always the case, but I felt it was more like we were learning how to use the ACI 318 book than doing, like first principle engineering type analysis like you might in one of the other fields of engineering. So you need to, that is important stuff. It's very important stuff for safety and for production. And if you're working in a firm, you can't be doing research and development every day. You need to be getting projects done. But I think one of the key things is to just not get too caught up in that and think about how things are really working. How do things really work? Do what it says in the code, but what's really going on here? The code often is an idealization of things, or a simplification. And with the structural plain concrete, or with advanced materials, the whole idea of this committee was really to make the performance-based provision for plain concrete more accessible to the industry, as to allow industry to innovate and develop better materials. So, you think about it, we've been using fundamentally the same type of concrete. I mean, there have been advances, but you could argue for thousands of years. Why can't we make concrete with, say we use, well, even let's take some incremental steps. Better quality control in plants than we had back in the 60s allows for more consistent mixes. Our resistance factors are based on consistency. Are we using resistance factors that are based on stuff from the 1960s, or have we updated that? Even the ability to like measure moisture in a concrete truck has come a long way, for example. But then think further than that. Think about like some of this nanotechnology and all these ideas. Could we make an additive for concrete that makes it behave more like steel, more isotropically rather than or less brittly? Helix is maybe just one little step in that direction, but ultimately in the future, could we develop concrete that fundamentally doesn't need traditional reinforcement? It could be reinforced chemically or reinforced with nanotechnology or engineered aggregates or different ways to reinforce that maybe we don't even know yet. And then those properties be used in a relatively easy way without having to go through a major, to get something changed at ACI, it's been described as a glacial process. It takes years, but the idea behind the plain concrete was to be able to say, okay, let's just make it so you don't have to use, there's a fixed ratio for flexural strength in the code. It's 5 times the square root of the compressive strength. Rather than saying that, be able to alternatively run an ASTM beam test to measure that strength So if you've got some nanotechnology additive, you put it in there, you run the test, and you get 10 times the strength, you can immediately use it, in chapter 14. So that was the idea. And, I think it requires people to really think about how can they challenge the way things are done. And if you're on the material side, it's about coming up with new materials. If you're on the consulting side, it might be coming up with different ways to analyze things that are maybe a little bit harder, but provide more, because they're not as simplified, they provide more, allow you to make the design, I guess, safe, but less conservative. And I think we'll talk about that later. So it's just a matter of just not being satisfied that the way we're doing things is absolutely the only way.
And I think that's a good point, especially for some of our younger engineers who are listening, because I know exactly what you're describing in engineering school. I remember my reinforced concrete design class. I remember my steel design class, and it was how essentially to use the book. And I remember my professor was like an adjunct, but he worked for a firm beforehand while also doing research. And that was one of the things that he imparted on us, is like thinking outside of the box specific, even though he had his course criteria of we had to learn how to design reinforced concrete with traditional reinforcement, not necessarily the helix or the additive. But he mentioned, there are restrictions and you have to oftentimes think outside the box to be beneficial to your firm, but also just beneficial to the industry.
Yeah. And could you talk to us about advanced materials and how they can be used in performance design, similar to what you mentioned earlier?
Yeah, so I kind of got out of order there a little bit, but so advanced materials, really can be anything that makes the behavior of the material better. And what I particularly focus on is the strength of it. There are a lot of companies out there that are working on durability, they're working on permeability, things like that. But what I'm really very interested in is how can we cost effectively increase the flexural strength of the concrete that we use, so that we then can use that benefit to attack some of the issues that we're faced with the industry. And some of those issues, just to be a little more specific, I mean, let's start with the very old school. It's cost. So I don't know, Kara, I heard in Texas, the cost of concrete is going through the roof. It's more than doubled where it was in recent times. And there's even rationing of cement in some markets, and I've even heard of jobs being delayed because of some of these issues. So if we have higher flexural strength, maybe we can use thinner, we can go with thinner designs. And I did an article, I was a co-author of an article in Structure Magazine that talked about how you can actually cut the thickness of a slab in half by using a combination of advanced materials and analysis. And those are things that I think in the past, a lot of engineers, particularly on slabs, and slabs are not the sexiest thing in the world to design, but a lot of times they're just cookie cuttered. In Texas, they have the famous Texas fours. It's typically a 7 or 8 inch slab with number 3s or number 4s at 12-inch centers, and that's what everybody does every time. There's not a lot of analysis that happens. So the other challenges are, I would say, maybe newer. Labor is a bigger issue these days. It's very difficult to find people who want to go out and put steel on the ground. Everybody wants to work in front of a Zoom camera these days, and people just aren't going into the trades. And then there have been supply chain issues. There's certain sizes of wire mesh, certain sizes. I've heard that you can't get number 3. Nobody wants to make number 3 bar. They all want to make number 4 bar if they're overbooked right now. So there's certain markets where you can't get number 3. So you just have to put number 4 in. That was not something in my earlier career that we saw. And then obviously the carbon footprint, and the Portland Cement Association put out and it's in my article, a roadmap for carbon neutrality. And they address some of these things, and they kind of point the finger at the engineering community a little bit and challenge them to do things like optimize the concrete mix. So that's where your advanced materials come in, avoiding over design, and also educating, which is what you guys are doing, which is great. Educating especially new engineers that are coming in to really think about these things.
Yeah, and to comment on that, I like the way that you mentioned maybe the technology of the future and ways that we can use material testing and even the advanced analysis, performance-based design analysis, nonlinear analysis. I know that's something that I learned in school. Instead of just using the code limits, we would get into more in-depth nonlinear analysis. I know it's getting more technical, but that is something that's used in some of these bigger high-profile projects where they need to optimize and they need to prove via testing or via advanced analysis that it's still meeting the intent of the code instead of just going per the code. And I think I've seen some studies where they do these more advanced analysis, more advanced, I think even some testing as well, that what you were saying, you can save a lot more materials, more innovation, and better performance in the end as well. And so, yeah, I think that's very interesting. And seeing even what you were saying with the nanotechnology, maybe even AI, maybe AI can help with mixing things, or who knows what will happen in the future. But things like that, it's really interesting.
Yeah. And on the topic of advanced analysis, when you think about a performance-based design, and I know Texas is fairly conservative, which is why we're very close to the code. I say conservative, that's not the appropriate term. They do more prescriptive designs just because we do have, you mentioned it, our workforce in Texas is, we have extremely low labor rates, specific around the concrete industry. And so sometimes it's easier to just standardize your construction to prevent any confusion. Because I remember when I was in Houston, I was talking to a contractor, and the loaded labor rate for an installer was $25 an hour, and that's the entire cost to fund the person. So I know there's restrictions around that, but you mentioned advanced analysis, and I think Matt made the mention, we're seeing it a lot on high profile projects, but I think we're also seeing it just with the restrictions in what you mentioned, the supply chain management, labor, material cost, all of that. Can advanced materials, if they're not being clearly defined by the code, be used in performance-based design? Or what's the most impactful way to use them for performance-based design?
Well, yeah, so that's a great question, Kara. And, when I took my reinforced concrete design class, I remember probably the first day of class that topic of performance-based design came up, and the whole idea of, really the whole ACI code is essentially performance-based. It's a deemed to satisfy, code that basically, sort of provides a method of meeting the level of safety and reliability that ASCE 7 is looking for all systems. But it's a good thing to remind, it's section 1.10 of ACI 318, and that's the performance-based design allowance. And it's there's a similar provision in the IBC and the IRC and pretty much any building code in the country. And it basically says that you can innovate, you're allowed to innovate, you can do things that aren't in the code, provided that you demonstrate that whatever it is that you're using, a material or a method, meets the performance requirement, or equal or better performance than what the code requires. So that's a pretty broad statement. It also says that the building official makes that call. So the answer to your question is absolutely yes. You could use anything. You could use spaghetti in your concrete if you felt it would add benefit, and you could prove it. It does, but the challenge is the practical aspect of it. How do you do that? And that's where like groups like the International Code Council, ICCES, come into play. They'll produce a third-party test report where all the testing is done in independent labs, and they'll basically demonstrate that in a short, concise report that's really written for the building official, that an alternate method or material meets the performance. And you're probably familiar with that because Hilti, was heavily involved with that before sort of the full codification, and they probably still use it for performance measures of certain anchors. But that's the challenge. And one of the reasons it took us so long to get the product to this level is because it's very difficult to demonstrate performance from, say, a PhD thesis to a practicing engineer like Matt. He doesn't have time to go through a 800-page PhD thesis. So, if you can get that down to a very short, 5-6 page report from somebody like ICC, the engineer knows that it's been tested and peer reviewed by a third-party group to meet a certain provision in the code, then it becomes practical to use. The problem with that is it's very expensive and time consuming to get those reports. And even with those reports, there's some engineers that are like, no, I'm only going to do what it says in the book. So, that's on one side. Now, on the analysis side, there definitely are ways, there are things that are allowed in the code, like finite element analysis, for example, is perfectly acceptable in chapter 6 of the code. A lot of people don't do it. They'll do a hand calc or whatever, and it might be fine, but you might be able to get another 10% if you do a more complete analysis. I think that's an area where we'll probably see AI come in to play. Having an algorithm that's really focused on optimizing things like carbon footprint, even, how can we reduce the thickness? How can we, maybe use some of these other materials like Helix in certain areas where it makes sense to achieve some of those benefits. And then there's some simpler approaches that have been around for a long time that often aren't used in things like slabs on grade. And, one of them is the yield line method. And that was one of the topics I covered in the article in Structure Magazine. And it's remarkable what you can do. The yield line method it's a nonlinear method. We actually learn a similar method for like column and like frame analysis, where you are redistributing. I don't know if you remember those homework problems where you had a bunch of columns in a slab, and you had to basically the moment redistribution.
Yeah, moment redistribution.
Yeah,
by hand.
Yeah.
Yep, with the tables.
I try to forget those.
Yeah, I think we all remember those, but there are ways. It's a similar approach for slabs, and it can be used in suspended approaches. And there's actually automated ways to do that. There's a really cool company in the UK called Limit State that has a software program that does yield line analysis. And, you can often get literally twice the capacity out of an equal system by using that type of analysis. And really what you're doing is you're redistributing the moments. And ACI is okay with that on certain structures. Like, I believe it's acceptable for yield lines, acceptable for foundations. They're a little bit more conservative on like frames, and there are certain ways that you can do it that they want you to do it, and certain ways they don't want you to do it. But just applying some of those methods can often reduce the thickness or reduce the amount of reinforcement that's needed in something. And it might take a little more work, but it's gonna make your client happier. It's going to be less money, and if they're interested in carbon footprint, often less carbon footprint.
And you mentioned some of the challenges that I'm sure you faced when getting and that engineers face as well, in terms of making those alternative designs or those performance-based designs a little bit easier to do. You were mentioning a lot of the challenges that it just makes it hard to do something innovative with regards to the code. Do you know of any specific ways or changes that could be applied to the code, or that you think should be applied to the code to make it easier and safer to allow for performance based design?
Well, I'll just give you one example, Matt. And this is kind of in the area that I'm kind of specifically working on. I'm the secretary of the ACI 380 and co-founder of the 380 Structural Plain Concrete Committee. Ultimately, what we would like to see is an option in Chapter 14 that allows somebody to submit a C78 flexural test. It's a 4-point beam test instead of a cylinder test. So that would allow a manufacturer, if they have, or a ready mix company, for example, to have a submittal, just like you see with your regular concrete submittal, that's a flexural strength submittal that says, okay, this mix has an 800 PSI flexural strength. And then they can develop that mix. They can use whatever they want to achieve it, whether it's a different composition of cement or additives or something like Helix. And then they can market it as having an 800 PSI, flexural strength. And then the structural engineer can use it. And keep in mind, the current approach probably only allows them to use maybe 300 PSI of that 800. So, and then the quality control's done. So it closes the loop. You can specify that beams are taken during construction, and you may be able to get away without using rebar and say, for example, spread footings in a warehouse building. And that's a tremendous time savings associated with, and it's a very clear, instead of this kind of nebulous, you can use anything for anything in the code. It's a little bit more specific. You do this test and you get a number from the test, and then you can use that value for design. And, ultimately my vision would be that this could leave a legacy on the market that would encourage people to design better materials. And you think about 3D printing. 3D printing is really challenging right now, because you still have to reinforce the concrete. If you could develop concrete mixes that you could essentially design using this approach, the plain concrete approach, which is permissible for walls, you get enough flexural strength in it, then you could just print walls and be done. And maybe even more as we get further along. But if there's not a framework in the code that encourages the industry to do that in a somewhat simple way, then it just doesn't happen, or at least doesn't happen very fast, because it relies on people who are really willing to push the envelope and do all that outside work to try to prove to a practicing engineer that this will work. So, ICC is one example of, that's kind of one step. The next step is providing a little bit more guideline within ACI 318 as to, like, in using the example of plain concrete as to how you do that. How many tests do you need to run? What does the average need to be? What's the resistance factor that you apply, etc.
So, and, you seem to have kind of worked through, it sounds as if you worked specifically with, as the manufacturer, because you own the company. And then to really see this change and innovation, you started working in the code body with the committees. Is that how you see as maybe the best method for, structural engineers? I think everyone aligns on that, sometimes the code is more restrictive than it should be. It's meant to provide a prescriptive, safe design, but obviously, a lot of engineers observe innovation in a lot of areas that haven't been adopted into the code yet, but they want to observe some of those benefits in their designs. And you mentioned, you started out with your company and then you developed an acceptance criteria for the testing to meet the needs of ACI 318 Chapter 14. Is that the method? So for a structural engineer who maybe wants to provide some innovation to the industry, is that how you see them having the most impact? Is maybe joining a code committee? Is it, maybe working specifically in the manufacturing process, developing the acceptance criteria to, meet the needs of the code? Where do you really see the most impactful place? Because I feel as though you've played all of the positions for someone who does want to see a change in the industry.
Well, first of all, you got to be persistent. I remember going into ACI. ACI is in Farmington Hills, about a half an hour from my office, like one of the first years I started. And they said, Well, normally it takes 20 years to get a product adopted, but we have a new fast track method that allows it for 10 years. And, here I was.
Sounds about right.
Yeah, maybe 29 or something like that. I'm like watching all these people like doing like these tech startups and, it's a different scale of time and you have to be patient. But I do think that the code and code advocacy is an important part of it, but unfortunately, those groups just won't move as fast as most companies can tolerate. So if you're out there trying to sell a product and you've got the science out of a university or something like that, it's very difficult to sell the product to industry based on university science. I do feel there's a really good place for building product evaluation reports in between the code and that university side. We have reports both under IAPMO and ICC. I developed a criteria with both of them. That is a very challenging process. It requires public peer review and all that. It's rigorous, but it's faster than the ACI process. What I think you need to do is you need to kind of get started. You need to get out there. I remember going out and selling our product for septic tanks and burial vaults originally, because there really wasn't much code stuff involved with that. But then we kind of built from that, worked on developing the data for the evaluation reports. That took quite a bit of time. Once we had the evaluation reports, we kind of turned the corner and we were able to do some really neat things in structural concrete. I would say that Helix is probably at the forefront of structural applications. Most of the applications do fall in those application restrictions of plain concrete. So they're walls, laterally supported walls, footings, and structural slabs, but we have tens of thousands of them. And these are applications that would typically require structural reinforcement. So having the evaluation report allows you to do that. But I do feel like, to answer your question, getting involved in the code committees and advocacy is important. But you need to if you just go and be a member of a committee, you're never going to get anywhere. In my case, I wanted to take things in a different direction altogether. I approached ACI about it. They didn't like it. I approached them again. They didn't like it. On the third time, they said, okay, we'll start this. We'll allow you to kind of start this 380 committee, the structural plain concrete committee again. I'm also an active member of 332, which is the residential concrete committee. And the other thing that's helpful, that's a really long-term play. Being really willing to innovate and approaching ACI and saying, hey, here's a way that I think I could help the whole industry. That's ultimately what got them interested in the 380. But then, just as a young engineer, participating and being willing to help, because when you help in those committees, the folks that are in charge are going to give you more of a voice. So if you just go and sit in the meeting, but if you're willing to kind of spend some time in the evening and do some calculations to support some committee work, for example, you're going to get more of a voice there. Be willing to present things there. It is a good forum to talk about innovation. It's a good forum, even if it's not something that's the code's going to adopt. The more you talk about it, the more people get interested in it. And that's kind of what's happened with the plain concrete. Initially, it was kind of a small group. And the more I talk about it, the more people get interested in it. And the committee's grown. We had a great session at the last committee. We're doing another mini session in this next committee where there are people coming in talking about, oh, here's a place I use plain concrete. Here's an advanced analysis method that we might be able to use with plain concrete. So it's a great way to kind of spur conversation. I definitely encourage people to get involved, but also look at the alternate pathway, because if you truly have an innovation, you're going to have to do something. If you wait for ACI, you'll go out of business before you sell any product.
Yeah, I think most building codes are follow that same route, even with the cities and when
Right.
the the codes
Yeah.
get out. It's like, yeah, I'm using ACI 14. Like that's 2014. That's like
Yeah.
more than 6 years ago. It's like, yeah, that's how it is. But yeah, because with regards to the committees that you were mentioning, it is what you put into it. You get what you put into it. And I know for younger engineers, it's tough for them to, or maybe they're more intimidated to get into those because they may think they're not smart enough or anything. But if you talk to a lot of the people like yourself, or even the ones that are heads of those committees, I mean, they all started somewhere, and for them getting involved, well, that's how they learned. They were involved, and then they would learn from those meetings and have some assignments, and they would do research, and that's how they get so good, and that's how they eventually become part of the committees too. And I think uh, like you were mentioning, encouraging young structural engineers to get involved in those, because if you don't, then I don't think you really have much to complain about if you're not like part of those. Because if you want to see I mean, sometimes we complain about, oh man, these codes are so complex, XYZ, they just keep getting bigger. Well, be part of the code committees, and you can be a part of that instead of maybe letting the researchers or the people that are in the committees just running those. Have your voice, get your voice heard, and be helpful, like you were saying. So maybe you can make a difference in the code committees.
Well, and I'll just say one other thing about that. I think the more practicing engineers that are involved, the better. I say the same thing with contractors. There's a lot of academics there, so it is a very academic thing. It's a very big part of an academic's life in structural engineering, is those committees and being highly placed on. But, remember, I'm not going to claim I'm part of it because I'm a material supplier, but Matt, you're part of, consulting engineers really need to be out there because they're the ones that have things to complain about,
Yeah.
In terms of implementing the code. And, for manufacturers like Kara and I, it's important too. And it does get a little mind numbing. It can be very political. People are trying to like jockey their product, like get standards that are, preferential to their product on the supplier side. But the intent is if there's enough participation and people are really participating and not just going there and sitting there and, so they get their, they can say they're on the committee, then it theoretically all that should be evened out, but it requires the participation.
And looking forward ahead into the future, what challenges do you see that structural engineers will have to overcome in the future?
Well, I think, Matt, there's a lot. I mean, I think that, the days of just kind of in the interest of time, just copying one design over to the next. And, like I see with slab design a lot, I do think that, there's going to be more pressure from clients and from contractors to really avoid that over design factor. And I think that a lot of times as an engineer, it's just safer, it's easier to kind of be a little bit more conservative. But given the scarce materials, given the scarce labor, the push, we have some customers that their number one thing is carbon footprint, and they want as thin of a slab as possible. And it requires us to really kind of sharpen our pencil, get more data, more geotechnical information, more details about where these posts are coming down, for example, on a slab, so we can really sharpen our pencil. And that could be perceived as taking a little more risk because we don't have as much factor safety in, but we have to be willing to do that. And we need to figure out how to do that smart, so we're not compromising, quality or safety. The other things I think as we look out into the future is being open to advanced materials, being open to new ways to do things. It's difficult when we're under pressure in a very busy consulting environment to think about that. I encourage you to do the lunch and learns, even if you think it might not be, make sense for the project that you're doing. Listen to some of the manufacturers and what they have to say. If you like what they're doing, reach out to them and get involved. if there's code advocacy that needs to be done to use it. And then I think the other frontier is where does this advanced analysis go? And, you know, Matt, you mentioned AI. What's that going to look like for structure? I've talked to 2 companies in the last year who are trying to develop basically structural engineer AIs, you know, that are trying to figure out, you know, okay, can you have an algorithm optimize an entire building design? I don't know what that's going to look like. That could be a challenge. It could be a great advantage, and it could free our minds to kind of do some of the stuff that's a little less routine and forward thinking. So we can think about it that way too.
Yeah. For just my comment on that is, I think in terms of the computers and AI, because that is a thing. I mean, we codified our stuff to the point where if you follow, you know, like what they teach us in coding school, if you learn anything about code, I mean, that's what the building codes are. So
exactly.
You could technically and that's what the computer softwares are doing. You know, they go through those code and what do you call it? That ladder, that tree where it's really procedural. So I think that is a challenge. And what I try to tell new engineers is, you know, learn your fundamentals, because if you don't know the fundamentals, I think someone, at least for the foreseeable future, hopefully not in my lifetime, but I think there's always got to be someone has to take responsibility for that computer, and if it's doing it right. So I think really getting a grasp on materials, the behaviors, the fundamentals of engineering and materials, and the communication skills, the human communication skills. I think that's what the engineers are going to look like in the future, in my opinion. They're going to be technical, but they have to be great communicators as well, because a lot of the tedious stuff, like that moment distribution, like that's going to be done by computers, and it's not going to be really helpful for you in your career.
Sure. No, I really like what you said about the fundamentals. And I really think that the stronger you are in the fundamentals, the better you're able to kind of really think outside of the box too. You know, really think about you're designing a connection or even a slab. What's really going on? Where are the loads really going? Where are the areas that you really need to be concerned about? And, you know, think critically about those things. And, you know, that's where you're going to get ideas in terms of, you know, making things more efficient, you know, lower carbon footprint, you know, all those sorts of things.
And I think that's really good advice, especially just to the engineering community in general, is, you know your fundamentals. That is key, because I think Matt is pointing it in the right direction. We are getting more and more with the code. Everything's pretty standard, but understanding what the basis behind the design is trying to do. And as you mentioned, knowing where all of where the issues could occur, or where you need to maybe strategize the majority of your time in order to optimize at some point. Is there any, we had a lot of great comments today, and but is there any final advice maybe to our engineering community that you have specific to maybe trying something out, specific to really innovating the industry, or maybe just kind of give them guidance in their career, because you seem to be making a very strong impact specific around this plain concrete topic? Do you have any final advice for them?
Sure, Kara, I appreciate that comment. I'm definitely trying. Yeah, I mean, I think it's a little different from each angle, depending on what your career path is. I'd say if you're in a firm, as I said, be open to these ideas. The folks that come in and do these presentations about new technologies, learn what you can, soak it up. Some of them aren't going to be useful to you. Some of them are going to be useful to you, and keep an open mind about those things. The more of those ideas that you have in your head, when an issue comes up on a project, you've got a catalog of sort of innovations and ideas that you can use to kind of attack those problems. I mean, remember, engineering is really about problem solving at the end of the day. And that's really what your clients are looking for from you. And the more tools you have to do that, the better. If you're approaching it from, if you've got an idea, I tell you one thing: be persistent, be patient. You almost have to will your ideas to success, because people will tell you you're nuts. Go back to doing what you're doing. Put your head down and keep working. Your idea will never work. Don't believe them. You got to be persistent. And at least until you reach a logical end. And use some of the approaches that are out there to, that the industry has to for innovation, like the building product evaluation report path. That's definitely something to look at. If you're practicing, definitely make use of those when they're available, because those make it easier for you to adopt the technology, because it's all there. That it's been peer reviewed, it's third party. It's not just a brochure that a marketer gave you. It's something that's been vetted. So be open. And then the last thing I would say is be vocal. Go talk about your ideas. Be willing to volunteer to give a presentation at ACI about something that you did that was innovative. If it was a design or using a product, those committees are always looking for these what they call mini session presenters. It's like a 20-minute presentation in a committee. They always want to hear from people who are doing things that are new and innovative, because that's what spurs the conversation and gets things moving. And it's a process you have to be patient with, but again, just you have to kind of will things forward at sometimes. So
Yes.
I don't know. Yeah.
No, I think that's great final advice, especially the persistence, because also with persistence, you gain followers. And once you have enough people behind you, it makes a bigger impact, especially on those committees and with those organizations.
Absolutely.
Yeah, and just getting through the old, I guess, some of the old timers, this is how we always did things. And
I would like to think that maybe they're not quite like that. I feel as though ACI and all of these committees really do want this new innovations. I think we've seen what the tech industry has done and, how they get things accomplished so quickly, but the tech industry is fairly new. So they don't have all of this overhead already existing from, being an industry that's existed for forever. So I think, and it's hard to cut that down when you have to, have so many processes. I think they do. I think, what Luke mentioned is they want to see these new things. They want to know what's going on in the industry with the future benefit of benefiting the industry. There's just so much overhead, I think, for those committees to get them adopted. I mean, the fast track is 10 years. That's crazy to me, but I know it's a reality.
Yeah, well, Kara, I'll say one more thing. And that's a great point. But, the code, it's conservative for a reason. I mean, you look at some of the failures that have happened and things like that, there has to be this process that's rigorous and, et cetera. But, you think about it, the concrete industry has really got some big challenges. There's more and more, pressure from other industries, steel and wood and other technologies that are, maybe, at least arguing, have better carbon footprint or sustainability. Think about concrete and its carbon footprint. I think the concrete industry needs innovators to remain competitive. And it also needs innovators to challenge some of the sort of these conceptions that, concrete can't be sustainable. It can. There's a lot of ways that a concrete structure, like, for example, the lifespan of a concrete structure is far longer than, some of the other technologies that are out there. But there are challenges and innovation is needed. And I think what you're going to see is that they're going to be more and more open to it. I don't know if you're going to see the process going faster, but I think they're going to be open to it, and I think it's needed, and I think they know it. So,
yeah, Definitely. I think that's a great point to make. Well, Luke, thank you so much for your time today. I really appreciated the discussion. One thing I wanted to get clarity for our listeners, you mentioned that you had an article in Structures Mag. Which subscription month was it?
Yeah, so it's in the April 2002.
Okay.
And it's well, that's going to be backwards, but yeah, and that kind of walks through the example of a slab on ground being designed using just a very conservative elastic approach all the way down to a yield line approach, and just how much thinner you can make the concrete, what the carbon footprint impact is.
Perfect.
So,
I think our listeners would really benefit.
Yeah.
You mentioned the yield line approach. I think after our discussion, they might want to review and look back at it.
Yeah, it's a little confusing, but once you kind of get your head around it, it makes a lot of sense, and it's been around for a long time and it works. So it's definitely a good tool in the toolbox.
Well, thank you, Luke. Thank you for your time today.
Yeah, thanks. Thanks, Matt. Thanks, Kara. Appreciate it.
Thanks, Luke.
Yep.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, which is episode number 83, as well as links to any of the resources, websites, or books mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcast. Until next time, we wish you the best in all of your structural engineering endeavors.